advanced form of X-ray imaging. So we still uses the X-ray, but now instead of the X-ray source being on one side of the subject, it rotates around the subject. So the detector and the X-ray tube rotates around the subject to generate the attenuation data. And this attenuation data is then fed into the computer to do the reconstruction, allowing one to generate an image that has got high soft tissue contrast, okay, unlike maybe what is in the case of conventional radiography. Okay, and then the other form, it is mammography. So it is a form of X-ray imaging that is optimized for imaging the breast tissue. So there's always a challenge because we are saying for us to distinguish the structures, it is on this basis of differential attenuation, comprised of structures that have got similar physical properties. Okay, so we need to be able to use low energy X-rays and optimize. Other than that, also the breast tissue, it is one of the most radiosensitive organs or tissues within the human body. So there's need of optimizing so that we are using low energy X-rays to bring out the difference in the, but also ensuring that the dose to the subject is not that high, okay? And then the last one, it is for dental X-ray. Also, whenever we have a problem with our teeth, we go to the dentist, they can also use X-ray. So the ability to distinguish different tissue structures varies in the different areas. Like I said, CT, computed tomography, is very useful for soft tissue. Differentiation mammography also can be used for purpose where you're having bone and soft tissue. Conventional radiography is sufficient. Okay. So other than that, that is on the basis of the physical structures. We may also use artificial contrast, okay, to enhance the tissue differentiation, to help bring out the difference between the structures containing the contrast media. So we can add contrast media such as barium and iodine, okay, contrast. Or during chest X-ray, we may tell the patient to inhale and capture. So when we introduce gas, it has a lower Z, so it tends to negate. So we say it is a negative contrast. So it's helping in differentiating the structures, okay, from each other. Okay, so we can also use the contrast. I think that will be the next topic that will be covered by my colleague, Dr. Iwak. Point is we're having the subject in between the source and the detector and what it is, whatever that is being transmitted. The second type of imaging modality is ultrasound. So it's here we are sending beams of ultrasound, the high frequency. So typically, so we can classify sound on the basis of the frequency. So we say the bit below 15 hertz, what we cannot perceive, and above 20 kilohertz, 15,000 hertz. Okay, this Hz is a unit of frequency, or cycles per second. That's the other. Hertz is a special name unit. Okay, so above 15 kilohertz is what we say it is classified as. But now for purposes of generating medical images, we go slightly higher. We are going in the range of megahertz. So between 1 to 20 million hertz. 1 to 20 million hertz, it is the range of frequency that is used for purposes of medical imaging. Okay, so here we send, so it means it is we are using the transducer, which is the source, and it is also the one that is used as the detector. It is on the basis of piezoelectric phenomenon, where some materials, they undergo mechanical, they deform and reform upon application of electrical energy. So when we apply a voltage across those materials that are referred to as piezoelectric crystal, or they will produce charges upon when they are stretched. So it allows one to convert energy from electrical to mechanical, as well as from mechanical to electrical. So when sending in the ultrasound pulse, we first apply a voltage pulse across the piezoelectric crystal that is within the transducer, okay, the probe. So it sets it to vibrate to generate ultrasound, then it is sent into the subject. So it will travel into the subject point where there is variation in the acoustic property. Part of the ultrasound beam that has been sent in, it will be sent back as an echo. So this echo, it comes back in the form of mechanical energy, and upon reaching the transducer, it sets it to vibrate, generating charges on the surface, and these charges are the ones that are picked, and then the electronics of the ultrasound scanner will use it to form the image. So in ultrasound imaging, if you think of the imaging chain arrangement, the source and the detector are on the same side. In fact, they are one and the same thing. Now the subject is on the other side. So for us to be able to form the image, it means there has to be reflection. So part of the ultrasound beam that has been sent in, it will be reflected. So here we rely on reflection, unlike X-ray detected by the transducer and measured, and the magnitude of reflected echoes and the location of the reflecting boundaries are mapped to generate the image. Okay, so like what we have. So when we are having a stronger echo coming back, it will appear to be brighter. Okay, and when we do not have any echo, it will be black, or when it is a weak echo, it will be dark. Okay, dark gray. Having a frequency of between 1 to 20. So this low frequency, it is useful for imaging deeper structures, okay, for like obstetric. Then for structures which are more superficial, we use the high frequency. Okay, that is ultrasound imaging. The third type of imaging, it is radionuclide imaging, or RI, or nuclear medicine, if you like. Here, radiation is introduced into the subject. Most often, for purposes of imaging, it is the gamma radiation. For purposes of treatment, it could be emitting a particulate matter. So particulate matter, it is coming from the nucleus, but it has a charge and a mass. So it is sent into the subject and then targeted to the organ that is of interest, and it delivers high radiation. Most often use the gamma radiation. Okay, so it is a radionuclide is introduced into the subject. Sometimes there are certain instances by itself, like radioactive iodine, it can be introduced to the thyroid gland, because the thyroid gland, it has an affinity of iodine. So we replace the non-radioactive one with a radioactive one. So it will selectively concentrate if with a pharmaceutical component. So in radionuclide imaging, we say we introduce a radiopharmaceutical. So radioactive material, it emits the gamma ray that is detected, while the pharmaceutical component, it acts as a vehicle that delivers the radionuclide to the organ that one is interested to image, okay, if it is for purposes of generating an image. radiopharmaceutical agent is known as radiopharmaceutical radfa. So when it is administered internally, so the patient, so we're saying it can be administered intravenously. Okay, it can be, if it is in gaseous form, it can be inhaled, or it can be ingested if it is in the form of capsule. Okay, so it is introduced into the subject, and gamma rays that are emitted by the radionuclide leaving the concentrating organ and can be detected externally. So in radionuclide imaging, we say it is a form of emission imaging because the radionuclide is introduced into the subject and the subject becomes to be the source of the energy. Okay, so we say it is emission. So it's the gamma rays, and then it is going to form. So dependent on the part that there is high concentration, it forms a hot spot or a hot cell within the image. So it tells you there has been selectively concentration. So one can tell whether the organ is working normally. This one of the advantages of radionuclide imaging is the ability to detect the stage. Early stage one can be able to detect, unlike for X-ray or even for CT that might require for anatomical changes to occur for one to be able to see the difference. Here at an early stage, at molecular stage, sometimes radionuclide imaging is referred to as molecular imaging. One can be able to detect. Okay, so here is an example. So we are having material. So the subject, and then they are placed in a gamma gantry of a gamma camera. So here it is having two heads. So one of above and the one anterior and posterior. Sometimes we have more than two gamma heads. We have the ones that has got three heads. Okay, and then one can form the image. So if an organ is small, it will be meant to be stationary for skeletal scanning to be translated. So the patient on the that is lying on the patient couch has to be translated through the gantry for one to image from head to the feet. Okay, so the spatial distribution of radiopharmaceutical is mapped, or the biodistribution of the radiopharmaceutical is mapped to produce an image, and that is on the basis of the location and the concentration of the emitted gamma rays. And hence, the reason we are saying it is a form of emission imaging. And the information from the radionuclide images relate to the chemical as well as the physiological status of the targeted organ. So that's why I said it is very useful for detecting functional physiological process within the subject. Okay, so they introduce a radiopharmaceutical to see how it is being transported. It is being excreted from the subject, like for renograms. So they want to capture if the kidney is functioning properly, they can introduce a radiopharmaceutical. Usually it is technetium 99 metastable. So it emits a gamma energy of 140 kilo electron volt that is detected. That is sufficient enough to escape from the subject to be detected with a detector that is external. So here the subject is the source and we're having the detectors outside. Okay, that is in radionuclide imaging. And the fourth one that I mentioned about, it is magnetic resonance imaging. So our bodies consist of water, large proportion. So we have hydrogen or hydrogen 1. So hydrogen 1, it's also sometimes we have a proton. It behaves like a magnet. And now when it is placed on external magnetic field, it will align itself in the direction of the external magnetic field or in the direction opposite, anti-parallel, parallel or anti-parallel direction. And also we use some radio waves or radio frequency radiation to generate the image. So during the de-excitation, talking of the proton, emit the radio frequency signals, okay, which are used to form the image. So here, dependent on the concentration of the protons or the hydrogen nuclei within a given tissue, it will have a brighter signal on an MR image that is on the basis of the concentration and also the de-excitation. So the de-excitation is where we have the relaxation times. Magnetic field, we say that is longitudinal magnetization. And when it is excited, it is flipped away by the RF field that is applied. We say that is transverse magnetization. So after withdrawal of the RF pulse that is applied during the examination or during the procedure, the transverse magnetization decays. So when one measures the signal due to the decay of the transverse magnetization over T2 signal, okay, and when one measures the regrowth of the longitudinal magnetization after removal of the RF field, the hydrogen nuclei within the subject will still align themselves in the direction of the external magnetic field. So that is the longitudinal magnetization. So when it regrows, we say that is T1. Either the concentration, what is referred to as proton density, to generate an image, or can use the measurement of the relaxation times, the de-excitation times, to form the image. Okay, so the most important MR-friendly nucleus is hydrogen, okay, say proton, but we also have the others which can be used, but their abundance is small, so that's why hydrogen 1 is. First, information on the basis of the hydrogen 1 concentration or proton concentration and the magnetic properties of the tissues being interrogated, okay, in the environment which they exist. So in MRI, usually the subject, mostly when maybe you rotate at radiology department in Kenyatta, I think they have a 3 Tesla. A 3 Tesla, it is a high magnetic field external magnet, okay, high strength magnetic magnet. So the patient lying supine, okay, so it is translated head, toe, okay, head to toe into the magnet, the ball of the magnet, okay. And then we have the RF pulse that are usually applied. So we said when we place the subject, the hydrogen nuclei within the subject will align in the direction of the external magnetic field, or parallel or anti-parallel. And when we apply the RF pulse, it excites to flip it away. And then that is where the signal is generated. And then when it is removed, one can detect to form the image, okay. So this is for MRI. So for MRI, we said we are using the latent. Okay. Now the last form of modality that I mentioned, which is where we are combining the two. So MRI, it has high soft tissue differentiation or high soft tissues sensitivity that can be rivaled by CT. But now for MRI, like I said, we are using an ionizing form of energy. So we can consider it to be a safe modality. So one, if it is available, one would use it. And it is the MRI scanner, they are not that, they are not really spread out. within certain specific areas. Okay, so each imaging modality, so they have high anatomical detail, and for radionuclide imaging, it has high sensitivity for the stage of the disease. One can be able to detect whenever there are molecular changes. One can be able to detect using radionuclide imaging. So one could combine radionuclide imaging and MRI, or CT and MRI, or what you will hear of CT PET. Now in Aga Khan, they are doing it, Aga Khan University Hospital. They are having a cyclotron that produces a positron emitter, and now they introduce into the subject, and then they take the subject into a CT, and we refer to it as dual modality. So PET, it is useful for sensitivity for the lesions, but it has poor anatomical details. If you look at the image, you'll see it is of poor quality, but sensitivity over disease process, it is quite high. Now for MRI and the CT, they have got high anatomical detail, but in terms of sensitivity, it may not be that high, as high fusion of the two. Okay, so to wind us, we may classify these imaging modalities. Okay, they have different strengths, the way I said. Okay, so we say we can classify them according to the unique features, okay, in respect of the nature of the form of energy. So in either are we getting physical information, chemical information, likely going to be paramagnetic, physical, conventional, we may also get. For chemical or physiological, we said radionuclide imaging, so it allows us to capture information about the function of the human body. So radionuclide imaging, or sometimes we have functional MRI, which can also give us information. The other thing that we can classify them, it is according to sensitivity, early detection. So we say there for sensitivity as opposed to CT and so forth. Okay, the ability to depict detail. So here in detail, vaguely mentioned, could be spatial resolution, ability to distinguish structures, seeing them as being separate, or ability to distinguish structures that are adjacent to each other on the basis of the signal size. So the appearance. So if it is bright, the brightness, that is tissue, sensitivity, CT and MRI, they have got high contrast resolution or ability. For spatial resolution, we may say conventional radiography, it has a high spatial, we can get more detail. And even in mammography, if we are using the film as our detector. Okay, the other one that, so uptake and excretion rate. So this is where we say for radionuclide imaging or nuclear medicine. So it is being accumulated in the targeted organ and how it is excreted. So one can be able to tell. So radionuclide imaging, like for renogram, one can get such information. And lastly, which now forms the basis for the next session, is safety into two groups of ionizing versus non-ionizing radiation. Okay, so I think this is the end for physical basis. Is there any question from your end?
Doc.
Yes, please.
Kindly repeat the explanation on the T1 and
for MRI. Okay, let me try to might use. So let's assume, because the patient is lying longitudinal, and mostly the type of the magnets that we are using, it is a superconductor. So because we want to have high magnetic field strength, like the 3 Tesla that I told you it is here in Kenyatta Radiology Department. So when we place the subject, direction of the magnetic field, usually it is in the direction of, when it is lying in the direction, we say it is parallel, and some of them will align themselves in opposite direction. So at that instance, we have created an MR signal, okay? But it is not used. We have to apply, because it is, we are saying it is, the magnetic field strength is quite high. We're saying it is, so that small difference, parallel and anti-parallel direction, will be difficult to detect. So there is need of applying an RF or radio wave, okay, because we are saying it falls within the range of the radio communication. So you see, if you're saying it is at 3 Tesla and then it is hydrogen, we have to determine the precessing frequency. One of the things, when we place the subject, the hydrogen nuclei. So precessing, it is rotation over rotating, or rotation over spinning body, like the spinning top. If you think of a spinning top, due to the influence of the gravitational pull, okay, so it will wobble. Okay, so it is the same thing also with the hydrogen nuclei or the protons when they are placed in the external magnetic field. So we need to apply an RF field resonance. The name resonance is to have maximum absorption and emission of energy. So it is applied at the same precession frequency. So when we consider for hydrogen, the precession frequency, we multiply the 42, there is a 42.58 times the strength of the magnet for us to determine the precession of frequency. So when we do that, in nuclei to spin away from the direction of the external magnetic field. That's where I said there is the transverse magnetization. Okay, so when the RF field is removed, so it means this the transverse magnetization that was introduced by application of the RF field, it will decay. Okay, so it means the hydrogen nuclei will be precessing and trying to align themselves in the direction of the external magnetic field that is always left on during the examination. Okay, so when it decays, so you're saying the transverse magnetization, it decays, it produces a T2 signal, because the decay is not instantaneous, it is exponential. So if we measure that, we say that is a T2 relaxation, or if you like, it is there is a defacing of the hydrogen. We say when they are precessing under the influence of the RF field, they will be precessing, they will be pointing at the same direction, so we'll be saying they are in phase. When it is removed, they will start to deface, so they start to interact with each other, they lose the energy, so between themselves. So sometimes also for T2, we say it is spin-spin interaction. So when we measure that it results to formation of a T2 signal. Now for the T1, because we said we have placed the subject in the external magnetic field, the hydrogen nuclei within the subject or within the structure or the part that one is interested to image, they align themselves with the direction or anti-parallel. So we have what is longitudinal magnetization. So it was, it had reduced when the RF field was applied, when the RF field is switched off, it starts to regrow. Okay, so that one is also sometimes we refer to it as spin environment interaction or spin lattice interaction, whereby the hydrogen nuclei, it emits the surrounding tissues environment that it is existing. So that one for the regrowth of the longitudinal magnetization is what is referred to as T1. Again, the regrowth, it is also exponential. So it can also be measured. And now, because the signal, it is coming in the form of an RF signal, so we can use an antenna or the coils, which are on the basis of electromagnetism. Whenever we are having a changing magnetic field, it induces current onto a coil that is nearby, or whenever we are having current, alternating current flowing in a conductor or a coil, it induces a changing magnetic field. Is that okay? Or
That's okay, Doc. Thank you.
okay. Okay, there seems to be none. So